All right, nerds. So we are now going to start our new topic, chemical monitoring and management, and we'll start this with having a look at the work of various chemists. All right, so what's the point? Basically, you want to be able to list three occupations that a chemist can have, and you want to be able to describe one in detail. We're actually going to give you two options here. You also want to outline a real life application of chemistry and the role of the chemist in that field. This kind of overlaps with this point here as well. And you also want to be able to outline why chemists will collaborate with each other. This is actually pretty simple, and we'll get there as we go. So what type of chemists do we have? Well, there are various types, and let's have a look at a couple of examples. So we've got the analytical chemist. He's or she is the one that analyzes the content of substances. So what's in it, basically, and this is often for maintaining product quality, but we'll talk about a different type of analytical chemist in a few minutes. You also have the nuclear chemist who produces and maintains radioisotopes. So this is used in all sorts of industries, such as food production, a lot of production basically, and often used for um, quality control. So then we have the industrial chemist. These are usually used at producing things. They're useful for producing chemicals in large quantities. Okay, so that's where your industrial chemist will work. Then you've got your forensic chemist. Now, your forensic chemist is actually an analytical chemist. So a forensic chemist will collect and analyze data to be useful in legal proceedings. Now, the forensic chemist he or she will analyze data, usually from a crime scene, to help with the prosecution case, or actually for the defense case as well. So they'll work for both sides. They're meant to be fairly unbiased. The forensic chemist will also work with the same tools as the analytical chemist because they're an analytical chemist, just for a specific, purpose. They'll make use of processes such as gas chromatography, spectroscopy, and a few others, but those are the two we'll focus on. So you want to use these processes um, when they're doing this. Forensic chemist is not working alone. Aside from working with other scientists, it's also going to work with the police and prosecution and a few other different groups of people. And it does this to identify substances and match DNA to usually put a person within a crime scene, as opposed to, the DNA really says this person does it. It's more a case of this person was here, and that then adds into the extra evidence with it. All right. So what is an analytical chemist? Well, basically, analytical chemistry is essentially it's the study of chemical compounds in identification and determining the properties. And once you know the properties, you can actually use those to identify certain chemical compounds. So analytical chemists, they'll use different types of analysis depending on what it is that they're doing. These can include a gravimetric analysis, which is essentially knowing how much of something. Gravimetric is to do with its mass. You've got a qualitative, which we can use to work out whether certain chemicals are present. So you're working on the qualities of it. There's thermal analysis, so we can see how it reacts with heat. For example, every pure substance has a specific boiling point or melting point. There's volumetric analysis such as titrations, and you know all about this now. So we're trying to use those to find the concentration of a certain chemical in there. So we can do these with different tests. Okay, you can use calorimetry. So if it melts at a certain temperature, it'll be pure. If it's got some, with alloys in particular, so if you change the composition, it'll move the melting point. Um, Chromatography, so you can separate into its individual components. You can tell if it's a single compound or multiples. And then you got spectroscopy, which basically you see how much light it absorbs. And we can use this, because each type of atom will absorb different amounts of different wavelengths of light, and we can work out what our sample contains. All right, so there's a calorimeter, which we've also looked at before. Chromatography, we'll actually go into this in a bit of detail with our forensics unit, and we will as well. This here is spectroscopy. So you can see here, you've got a light source, you've got a mirror, a lens to focus it. This is actually a filter which takes out most of the bands of light. It goes through your sample, which detects which bands of light actually made it through, which then is amplified, so you can lift up the sample, read what's in it, and then you read it, which is pretty cool. So let's have a look at chemists in the plastic industry. So when we're making plastics, we're talking about using petrochemicals. Um, and we're going to look at the specific role of a lab manager in a plastic factory. Okay, so in this case, we're talking about one that produces polyethylene. Now, someone working, the chemist working in that, in particular the lab management, they will need to use computers to predict the properties of the polymers based on different copolymers, temperatures, and catalysts. So, how it's being made. They've got to predict the properties. They will constantly monitor the equipment that's making it. So you want to ensure that you've got your materials are at the right conditions. Okay, reactants are maintained. Everything's pure. Sorry, the purity of reactants are maintained. Um, Impurities can actually interfere with catalysts in a very large way. So we need to make sure that our catalysts remain pure, and basically we also want to make sure that conditions aren't changed. It's maintained at the optimum levels. Okay. So we also want to carry out quality control at the end. So you can use this basically, a chemist at this end will um, use the properties, the physical and the chemical properties, to make sure if it is the right, polymer. Okay, so the example here is viscosity. If you can stretch it, or if it's viscous enough, then what will happen is you'll have a polymer that will flow into a very thin layer. Okay, so that's why you want it to be viscous. You want it to flow into a very thin layer. If it's not viscous enough, it won't flow. It'll just wash away. So you can work out the density to see if it's going to, if it's a high density or low density. Okay, so if it's got low density, it has very few branches along the chain, and this allows us to make LDPE, and that's what in this case the factory is trying to produce. You also want to evaluate the process and work out whether or not we're having contamination issues, whether um, the product we're getting at the end is what we need it to be. Okay, so we also want to know if we're making it at the most efficient way possible. Is there a way to make it more efficient, thus increase the profits for the company that we're working for? So you can actually do this. There are various different levels in the lab. Okay, there is the TAFE chemical technician course. All right, that's cool. But there are also people with degrees in chemistry and engineering, and they all do different jobs, and they all work together. Usually, the laboratory manager will be a PhD in either chemistry or chemical engineering. So let's have a look at a production chemist. So we've got one in particular, Jane Smith. In other words, we've made her up. Um, she is a production chemist at a plant producing ammonia, which is just here, through the Haber process. Um, the branch of chemistry she undertakes is analytical chemistry. Okay, so her job is she's going to work out what's in the final result and also what's happening at different points in the process. So she wants to use solubility, and this is so she's going to employ the principle of solubility. We're directly addressing a dot point here, because she's going to use gas liquid chromatography to identify the substances present as the gas is passed over a liquid stationary phase. We'll go into this in more detail. You do not need to understand the Haber process yet. You will, but right now we're just sort of doubling up a little bit. So she needs to know how soluble it is as it passes over a liquid stationary phase. So if we've got a high concentration of noble gases, the ratio of nitrogen to hydrogen is not roughly 1 to 3. The efficiency will be reduced. So she's worked this out through gas liquid chromatography. And if you've got CO or sulfur present, the catalyst itself might be poisoned, which means we're going to need it to replace. So if she detects that there's carbon monoxide, she can then, inspect the catalyst and see if that needs replacing. So that's essentially an analytical chemist or a production chemist, but an analytical chemist working in industrial chemistry. So, why then will scientists collaborate or chemists collaborate? This is really important as well. So you need to do it because efficiencies increase. So you've got more people. Um, if you've got something like the Haber process, it's actually it's a many step process. So if you've got different people working at different stages of it, you don't need to move from one stage to the next. You can just keep it running as it goes. Um, Not every scientist, not every person, and you'll know this in your lab groups. Not every person in each lab group has the same set of skills. Um, the more specialized you become, however, that you know your particular area of expertise, but you're outside of that. If you want to work on that at the best level possible, you're going to have to get other specialized scientists, other specialized chemists that understand each different step along the way. And that's it. That was a long one, so hang in there, and we'll see you in class.